Hi, thank you, everyone. It's really great to be here. Over the break, I was also looking at a little bit my history with PyData because it's a really meaningful moment for me to be standing here giving hopefully a little bit back because I looked what the first meetup that I went to from PyData was in 2014 at Pivotal Labs, a little over 4 years ago. I've been to 20, at least according to Meetup signups, which I'm not sure if that's good, always a good estimate, but about that. So it's really meaningful moment to be here now after like this meetup has taught me so much, because I remember being here. I was at my first data science job, proper data science job, I guess. Starry-eyed, you know, like thinking about unit tests, like why would I write more code that tests my code? Oh, those were the days. But anyway, so it's really great to be here. I also was surprised to find out that my previous speaker was also Czech. And I met another Czech in the audience randomly, so this meetup is becoming a real checkbook exercise, if you will. Anyway, okay. So before we get into the nature of the talk that's just disappeared, I just want to have like a little bit of sense of who here has heard of a GAN, a generative adversarial network. Perfect. Who knows what a GAN is and could like kind of describe it? Raise your hand. All right, yeah, that's good, that's good. Who here has ever implemented one or played around with one? Fewer? Yeah, okay, then maybe this is a good segue. I mean, this is a specific paper. It's one of the like cutting edge ones. It's been presented at ICLR 2018 in Vancouver, I believe, or somewhere in Canada in April and May. So this is really cutting edge stuff because it's just been presented. So about myself, just very quickly, I mean, I kind of see myself like as an educator. I kind of like the sort of explaining about concept like really, really simply. So I teach at like a couple of universities, obviously not as a professor, but like it's just part of their like continuing education, that sort of thing. So I really like doing this kind of stuff, hopefully like usually in a much smaller setting. Anyway, so that's just briefly about me. Currently I'm working as like an R&D data scientist at Modano. So let's get to it. What is generative modeling and why is that an interesting problem? So basically, I think everyone here is familiar with some sense of sort of discriminative like machine learning. That's typically how we all get introduced to any kind of machine modeling problem. We have some sort of function or some sort of model that we're trying to basically estimate its parameters to get out a prediction, right? That typically is some sort of classification or something like that. Now, generative modeling obviously falls into typically falls into unsupervised world. So no longer are you in a space where you have a clear set of labels, but you're instead trying to learn this like sort of learnable function generate, right? That is what we're trying to accomplish with a lot of the machine learning generative models, which obviously there are also analytical ones, but these are the ones that we're going to be focusing on today. So ultimately, it's all sort of derived for some maximum likelihood. You're trying to basically maximize the likelihood of your data being real, right? So on a sort of conceptual level, what we're trying to get to is, okay, so there's some data, and we're trying to create some sort of model that when you run in through that, this magical function that we are not like looking into too much for now, just generates out something that looks real, right? Like that's the broad objective. And obviously there's like different paths, like explicit models, which are like pixel RNNs and all sorts of things. Variational autoencoders are in fact what you see here. They're kind of like some way of generating MNIST, which is really like the hello world, right? Like the handwritten digits, and slowly getting better and better results, right? So I think that's kind of what the machine learning part of generative modeling is really about, right? Like we're trying to improve the way our examples look iteratively, right? So the explicit is probably closest to what most people know, right? So you have some sort of loss function, and you're trying to really optimize that. So VAE actually has like an explicit loss function. The opposite of that is the implicit part, right? So in this case, like something like a generative adversarial network has there is no clear measurement by which we can say, yep, this is a good GAN. And actually that's one of the larger problems in generative adversarial modeling is that we have there's just starting to be metrics of how good of a visual quality of a sample that is. So by the way, I just had a question in the break, like GANs can be used for lots of things. I'll just talk about imagery because that's by far the most mature field within GANs. Right, so obviously, how do we even estimate this like maximum likelihood problem that's like the function ultimately is pretty complicated, right? So how do we even go about that? So we can use a generative adversarial network. So I think this is like the first time we'll kind of go over it. And we'll look at it in a couple of different ways because the concept, I think when most people encounter it, starts to be, it can be a little bit unintuitive. So basically we always start out, can you see my mouse? Okay, cool. Obviously we have to start with some training data. We don't need labels, we're in an unsupervised world, so that's all good, right? And I think there's the concept is, there's basically three parts, right? So networks, so that's the third word. So there's two, obviously. So there's the generator and the discriminator. They're adversarial, so they're competing. We'll talk about that. And they're generative, which we already talked about, right? So the discriminator itself is basically just a supervised algorithm, right? It has to make a binary prediction, right? Real or not real, fake or real, right? So it's just 1 or 0. So that's pretty simple, right? We kind of understand this from the supervised world, right? Like this is just a more complicated version of some sort of classification. This is just a part of a classification model, right, within a more complicated setup. So the generator is typically of more interest and is typically also more complicated. So we understand that like we kind of have some like seed, like random seed. So that's basically what this latent sample is. So you sample from some random distribution, you run it through some magical function, and that gives you something that looks real or not. Like it just kind of generates something in the first instance, right? Like you just initialize the model. It's not very clear that it should be any good, right, at this stage. So there's this process that then the discriminator starts to do. So the discriminator is basically sometimes seeing the real data and sometimes seeing the fake data. And because of that, it gets better at recognizing what looks real and what looks fake. So obviously, it kind of starts to look at, OK, so this starts to have some cohesion, whereas this generated example does not have really like any sort of consistency. It's just a bunch of random points, right? So it basically generates a feedback that then gets back propagated through the generator. So basically itself like is its own stochastic gradient. So obviously update. So doing this loop, it gets better over time. And then you have the generator, which also has another separate loss that's independent of the discriminator. And both are basically trying to beat each other because they're competitive in some way. So I know that's probably confusing, so let's go through this in a different way. So what does that mean? So a generator basically takes in a vector of random numbers, and then basically tries to create examples that are as convincing as possible, right? So you're trying to basically minimize your loss by convincing the discriminator that your examples are real, right? And then obviously that the byproduct of that is that the data that you generate are indistinguishable from the data set, right? So we're still in unsupervised world. So the generator actually never ever, if you look at this, gets to see what the real data looks like. What it gets is the feedback from the discriminator. And then the discriminator basically gets the two types of data, either the fake one or the real one, and the objective is basically to tell which is which. And then that's what we're trying to generate. So a helpful analogy to think about this is kind of like you have a painter who's trying to basically create like a lost piece of Da Vinci or something, right? And you have an art critic who's trying to distinguish what work should go into an art gallery, right? So when you take this sort of amateur painter who's like the generator, they're trying to, obviously, they're first going to come up with something, and they're not very good, so the picture is like all over the place, right? The next step that they do, they submit it to the gallery, and the discriminator, the art critic, says, no, this is not any good, right? So that way, the painter gets to learn, right? The amateur painter gets to learn, OK, I need to improve. Maybe they get some feedback on like what are the broad, high-level problems that they need to address in their next work, right? and maybe that work gets better, and so it passes the art critic next time around. So hopefully, by this point, it's starting to make a little bit more sense. And basically, like, it kind of creates this competitive dynamic, right? Like, they're trying to fool each other, right? Like, the same way an art critic might try to best, you know, for some ego reasons or whatever, like trying to beat this amateur painter who is trying to then deceive him because they're, you know, I don't know, they're trying to make money or something. Okay, so there will be some math, so don't, if you were terrified like I was from the last talk, don't be. Because I'll explain this in a lot more detail. So basically, there are two loss functions, right? We already talked about this. They're competitive. So there's the discriminator, which, you know, when you look at it, okay, this is kind of confusing, but there's some logs. We can forget about those for the time being. There's some halves, whatever. But basically, it's expectation. Okay, so that just means, like, you know, as we kind of go towards the limit. And then, but what's really important is this bit, right? Like, you can kind of make out like almost a traditional binary classification loss function in here, right? So this is the discriminator, and what we're saying is, okay, so we're basically trying to you know, optimize for this value so that we're accepting, you know, we're minimizing this quantity where we're accepting the real examples and we're rejecting the examples which were generated by the generator, right? So this is just the generated part, right? So g of z is the latent space vector, right? So we take some number that gives us the g of z, gives us the actual example, which we then run through the discriminator, and hopefully, you know, a good discriminator would tell that this quantity should be quite low and this quantity should be quite high, depending on depending on whether the sample is real or fake. And then in the original formulation, it's been formulated as a game theoretical framework. So there's basically, it's a min-max game. So I don't know if for those of you who are familiar with game theory, it's basically like you're trying to basically play a complicated version of Prisoner's Dilemma, right? Where you're trying to basically best the other player in this sort of competitive game without sort of and thereby improving at the actual generative process, which is a side product, but that's actually what we want, right? So in this case, the generator in the original formulation is literally just negative of the discriminator. So that formulation has a number of problems. I won't really get into them, but basically it's about like saturating gradients and generally being very difficult to work with that type of GAN, but it is well theoretically founded. So what even Ian Goodfellow, the author of GANs in the original work, came up with, is this non-saturating objective. So this is the one that people actually use most of the time. I mean, there's actually an even better improved version called Wasserstein GAN, but let's not get into that. So basically, in this case, you can kind of see, again, there's a degree of similarity, but they're now independent of each other. So it's more sort of tractable. Now you have this concept of, you know, I think the key takeaway from the slide, I'm also kind of running out of time already, is we need to, these two things look pretty similar, right? So just the second part and this, so that's basically the key insight, right? Like they're still kind of directionally, these two are still directionally equivalent, but they're no longer sort of just, you know, directly dependent on each other. But it preserves the competitive dynamic. So the training is iterative. So I think one thing that maybe trips people over sometimes is like, okay, but how does the discriminator know anything? How does the generator know anything? So obviously, you have to think about that this gets better over time. So both the discriminator and the generator have a sort of, you know, training loop. And obviously, both of them start out being relatively bad. And the early samples you'll get from the generator will be bad. And the early decisions that you get from the discriminator will be bad. So it's basically about like creating this loop through which that kind of one by one, sort of both of them get better over time, right? So hopefully that this kind of makes some amount of sense at this point. Yeah? Yeah, okay, good. Right, so why is this an interesting problem, right? So largely unsolved. There's a bunch of AI celebs that are saying, like, look, unsupervised learning is the future. I think you can kind of start to see why when you look at how difficult it is to get labels, and in like most of our day-to-day jobs, like we run across that problem. There's not enough data, or there's not high enough quality. There's all sorts of problems, right? And typically, like, this is like the pictures that you can see here are like generated by variational autoencoder, which I think is like in many ways the closest predecessor to GANs, because they're kind of generative models, and they're very blurry, those pictures around the edges especially. There's a reason for that, but I won't get into that. But you know, they're not very high quality. They're not that great. But they kind of started the generative modeling paradigm. They're basically unsupervised as well. And there's kind of lots of interesting applications that you can do, and we might get into that towards the end. But okay, so what do GANs? What are GANs? What can they do actually? So what you can see here, this is actually the work from the paper. These are all generated synthetic examples. 1000 by 24 by 1024 full HD images that are completely synthetic, right? And you can actually, if you go to TensorFlow Hub, you can download a pre-trained model, a bit smaller than this. I think the largest they have is 128 by 128, and you can run it on your local machine, right? And that's incredible, that you can actually generate examples of this quality with just basically 3.5 years after the technique was even proposed, right? So we've beaten the state of the art from variational autoencoders, and here we are. So what have the researchers at NVIDIA? By the way, the name of the lead author is Keras, which I think is spelled differently, but I think like that's how you know you're like destined for deep learning, right? Anyway. So what is a GAN doing, right? Like, okay, like we have all these latent space, and we can like interpolate in it and then generate all these different examples. This is also from that paper, by the way. What does that mean? So basically, there's this manifold assumption, right? Like you have the latent space, and you're trying to basically, when you run that through some generating function, you're trying to like capture some like parts of the manifold of where the real samples live, right? Because that space is obviously much higher dimensional than your seeding vector, which is typically of like 100 dimension, like not very much. So I think this is like a very neat way of thinking about it. Like, and actually these graphics are from his presentation as well. They're all in the references, by the way, so you can take a look at them later. But like you can think about the manifold as like an archipelago, right? Like it's like a bunch of islands. Most of the mass is water, like generally not good examples, right? Like you don't want to be there. You want to optimize your generative function so that it maps onto the islands, right? Like so this sparse space that's kind of like not very intuitively distributed in our heads, obviously. So we just kind of want to push it so that the examples that the generator generates consistently come from those islands, those good examples, right? They look quite realistic like those ones, rather than the ones that kind of like look kind of off, right? These are kind of like, what is that? That looks weird. So we want to just twist that kind of that generating process. Okay, so lots of math, scary. So basically, what they have proposed is this progressively growing of the network. So basically what they do is they manipulate this sort of loss space, right, by changing the complexity of the two networks. So we still have our loss function. So this is actually one of the improved one Wasserstein GAN, but it's still the same concept, right? So you can imagine your generated sample as a surfer, right, and you're trying to push him to the island, right? So you have this tool, the discriminator has this tool of those waves, right, manipulating the loss space so that the generators push towards the good examples, right, push towards the land. So the idea is obviously as we kind of manipulate this loss that we are introducing these penalties that kind of automatically guide us towards what we want to do. Well, so I think maybe a better way of thinking about it is, okay, so this is like where we get to at the end, right? So we're generating full HD images. But actually, that's still really difficult to get to that space. So what we want to do instead is we kind of want to like look at much lower dimensional representation initially to help inform the model, right? So we don't start with this really, really high dimensional manifold that we're trying to optimize, because that's confusing for the network as well. And in fact, stability is a massive problem with GANs. So instead, we kind of like start with something much smaller, right? And then we progressively grow it back, right? So we sort of simplify the space first, start pushing the surfer, the good examples, towards the shore. And then when we're more comfortable with the training process, we can introduce the extra complexity back, right? So, so basically, like, this is kind of how we start. And then as we, Okay, yeah. So and then so this is kind of the iterative process, right? So we introduce those extra layers, we double the size. So it's basically two, like, convolutional and what's called transposed convolutional or deconvolutional sometimes, but people don't like it when they say deconvolutional, so say transposed. Anyway, so but it's basically the same process, right? So you're trying to like upscale, generate the samples from a latent vector that's of a different representation, different dimensionality, and you're trying to increase the complexity so that you eventually get both like simultaneously a very complex models on both ends, which can generate those beautiful images, right? So okay, well. So we are introducing these extra layers, and they're double the size. How do we do that? That seems like that would like introduce a shock to the system, right? And you'd be right. And that's why there's another sort of neat addition from this paper where they kind of upscale with some sort of like bicubic upscaling or some simple algorithm, right? And then you smoothly interpolate between the two versions, right? So you start off with a very you start out with just an upscaled version of the 4x4 in the beginning, right? And then you start to introduce the extra layers, and you start to compose that image that the discriminator gets to see as more and more to be generated by the actual already upscaled layer, rather than taking the 4x4, upscaling it with some like non-parametric algorithm, and then and then feeding it to the generator, to the discriminator, sorry. So hopefully, like, we're just basically trying to avoid the shock to the system, right? We're trying to smooth it out with some like alpha that we kind of vary through the training time, and as we get more confident, we kind of get rid of that, and then we move on to the next layer, right? And we do 16 by 16. Right, so variation. So this is actually a picture from another paper that came out like 3 or 4 days ago. But basically, variation is another massive problem. So I think I won't go into the work that the guys have done in here. But basically, what GANs suffer from a lot is something called mode collapse. So mode collapse is where the GAN kind of learns a couple of examples that are all very similar to each other. So we're trying to basically spread them out. And they have introduced this neat extra statistic that they give to the discriminator as a helping tool. I don't think I quite have time to go into that. But his talk is also online, and you can read it in the paper. So yeah, so many batch standard deviation. But I just kind of want to cover like a little bit of the context, right? So GANs have had like fantastic couple of years. There's now over 1,000 papers. I think this graph only shows like 500, but depends how broadly you define GANs. Because once you get into the advanced architectures, it starts to get a little bit crazy. There's other innovations that this paper introduced, and it's one of the reasons why it's one of my favorites, is because actually the amount of like problems that they solve with a lot of their techniques, not everything is the best it could be. Like other people have produced like better training mechanisms or better metrics, but like these guys have done an absolutely phenomenal job of sort of solving a lot of the problems that existed in GANs at the time. This was the first GAN model to made it into TF Hub, which is a Google sort of repository for pre-trained models. So you can go and run it in your local machine. It's actually just like a couple lines of code. It's very simple. But so yeah, so there's a lot of work that's being done. I kind of wanted to show just a little bit of how what does actually this progressive growing give you? Like what are the actual effects, just for comparison, right? So you can see kind of it's like you can really see how the layers are being added, And you can kind of see that it's a lot more stable than if you just started with the fixed resolution. So you can see that our predictions, our just intuitive understanding has kind of matched what we observe when we look at the actual generating process, right? So that's quite exciting, which doesn't always work out that way, but awesome. I don't think I have time to run through the code. I just wanted to talk to it. So these are the references if people want to take a picture. Right. Yeah, well, we can talk about that later. OK. Right, anyway. So, yeah, the references for sure. OK, cool. Also, as I kind of hinted in the beginning, I'm writing a book about this. You can get it at that address. If you feel like that's too much, Cholet has also written an amazing, amazing book. And we're kind of trying to write it so that, me and my co-author, that it's actually at the level where almost after finishing this book, you can pick this up. If you do that, you're probably going to have to Google a lot. But it's almost possible. So that's kind of how we're trying to aim it. Also, we're hiring for client-facing data scientists at Modano. So there's my email address if you want to. But yeah, I think that's everything. So I think I even made it on time.
Thank you, Jacob. Right, well, we probably do have time for a couple of questions. Any questions, Jacob? Lovely. Microphone nearby you. Sorry, this action doesn't work. Yes.
Hello. Hi. Thanks for the talk. I was curious what the relationship between GANs and some of the reinforcement, actor-critic type models is.
Right. Yeah, so that's a great question. So there have been a couple of papers trying to connect the two. Especially work by Fao, I think, who's at DeepMind. I don't know the details of that work. There's already over 1,000 papers, so I obviously don't know all the details of all of them. One thing I'll say though is what I've touched on, and you can kind of see it in the progressive GAN paper, but more importantly, one very popular way of framing the GAN problem is something called the Wasserstein GAN. And Wasserstein GAN, so they kind of borrow a lot of the underlying maths from reinforcement learning, and actually they kind of rename the discriminator to be a critic rather than a discriminator. So they try to unify the terminology with that world. But I think so I think Fao 2016. I don't quite remember the name, but basically connecting actor-critic methods and GAN, something like that. Okay.
It's really similar to actor-critic because they also have two things, which is not the discriminator and the generator, but it's the actor, which is the generator, and the critic is the discriminator.
Right. So yeah, I think that's probably the best place to start. I think there have been other examples. I just I haven't had time to read all those papers.
Lovely. One more question, perhaps? Lovely. Question over here. If you want to grab a microphone, good. Button.
Hey. Generating samples is fun, but most use cases, they really care about